Hello there, eighth graders. Today we are going to put together everything we've been doing with linear and making sure if we have one representation given to us, can we find all the other representations? What does knowing that it's linear do for us? What mathematics can we do with it? So we are going to fill out this page called Linear Patterns in Context. It's page 78. Get your pens, pencils ready, and here we go. First, this cutest ever Quinny pup would like to say hello. Hi, Quinn. Hi. You say hi? She's just chilling. Okay, recording at home means recording on my phone, and that can make this a little weird, but we're gonna just go for it, hope for the best. All right, on the top, let's review a couple things here. For each scenario given, determine the initial value and the rate of change. This is stuff we've been practicing a lot. So Ray gets paid $5 per car she parks plus a $50 sign-on bonus. Well, that $5 per car right there sounds like the exact language we use for rate of change. So I'm going to write that on that line, $5 per car. The initial value is this starting point, a $50 sign-on bonus. Remember the language behind that. That means it is $50. Every time I write, this camera is going to be wiggly. $50 at 0 cars. Remember, that's the language behind the rate of change, $50 at 0 cars. All things linear here. Okay, number 2, a plant shoot was 4 inches tall when planted, and it grows 2 inches each week. 4 inches tall when planted means 4 inches at 0 weeks. Kind of out of room there, but I got to get all that language in there. 4 inches at 0 weeks, and the rate of change is 2 inches per week. Inches is an accepted abbreviation in the world. I did not make that up. So we use accepted abbreviations, 2 inches per week. So that's just a quick review, making sure we understand how to interpret rate of change and initial value. And also let's remember, hopefully we're connecting all this now, but initial value is really just b, the y-intercept, and rate of change is, of course, n. All right, now before we read this, actually, just kidding, we're going to read it first. Courtney is collecting coins. She has 2 coins in her collection to start with, 2 coins in her collection to start with, and adds 4 coins each week. Complete a graph and table to show how many coins Courtney will have after 6 weeks. Okay, so this that I'm giving you right here, we're actually going to come over here on the side to this question/notes, and we're going to make a list for ourselves to remind us that there are many different ways to write functions, and that includes linear functions. So if I have, I'm going to write this over here, linear representations is the word I'm going to write, but I'm not going to be able to fit it all in this little column. So I'm going to write represent/ations. But that word is representations. So linear representations. There are 4 main ways that we will represent a linear function. Okay, 4 ways that we can do this. And we are going to list them here to make sure we remember them. All right, so what I just gave to you is I gave you something that we call a context. And this orange marker is almost dead. Okay, so a context is a story, right? So you can have a linear representation that's just given in words as a story, as a situation. And you can see what we're going to do with that story is we're going to change it into a lot of different representations. So we're going to take that story and we're going to make a graph out of it. So there's another linear representation. We are going to make a table out of it. And we are going to make an equation. So you can have a context graph, a table, or an equation. Okay, let's try this. So Courtney is collecting coins. She has 2 coins in her collection. You know what I'm going to do? I'm actually going to make the table first, because sometimes once I've created the table, I can see a little bit better how to turn it into a graph, because when they give me a table, I usually call this first one X and this second one Y, and I think of it X axis and Y axis. Okay, so time in weeks is going to be, well, that's the independent variable. So I'm just going to go 0, 1, 2, 3, 4, and 5. And of course I start with 0 because 0 is always the true starting point. Okay, so at time 0, let's read this again. Courtney's collecting coins. She has 2 coins in her collection to start with. That means at week 0, she has 2 coins. Okay, then it says she adds 4 coins each week. This is my initial value. This is my rate of change. It's just the Amazon guy, Quinn. It's just the Amazon guy. She gets really upset when packages get delivered. Okay, so 4 coins each week. She'll chill out in a second. So 2 plus 4 is 6. Thanks for protecting us, Quinny. What a good girl. Okay, and then we add 4, and then we add 4, and then we add 4, and then we add 4. Okay, so I am now going to come over here, and I'm going to label on this. This is time in weeks. And this is number of coins. Now I can see on my screen that my hand is delayed from the other. I don't know if it'll be like that in the final recording, but we'll see. How exciting. All right, so time in weeks, I'm just going to go, this is 0. As you know, I don't like to label every single one. I feel like it gets squishy. It is going to go by ones. It truly is going by ones. I'm just not labeling every single one. Okay, so I labeled 2, 4, 6, 8, 10. But the in-between boxes are ones. Now, notice this over here goes up to 22. So let's think about this. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm probably going to want these boxes to actually each represent 2. So this is going to be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and then the top one would be 30. Okay, so that video is like freezing and catching up. Is it going to be like that in the final thing? I don't know. So now I'm going to, oh, I get it. Hey, look, there's a picture of me and my husband. It's because my camera went to sleep. Such a fun adventure. Okay, so 0, 2, there we are. 1, 6, 2, 4, 6. And I could keep using these ordered pairs, but I also know that this is just going up 4 over 1, up 4 over 1, up 4 over 1, up 4 over 1. And I can just follow that slope pattern because that's what linear stuff does, right? Follow that slope pattern. It's a linear relationship. It's going to make a straight line. It's going to follow that slope pattern. Okay, so here we made a graph. We took a story, we made a graph out of it, we made a table out of it. Now we are going to write an equation out of it. Now, they actually didn't use X and Y. They used C for coins and W for weeks. So I am actually writing a Y equals MX plus B equation, but instead of X and Y, I'm going to use the variables as they defined them, W and C. So C, the number of coins, is 4 per week plus the 2 she started with. So it's still initial value rate of change. It's just instead of X and Y, we use C and W. Okay. Is this context linear? Yes, absolutely. Well, how do we know? There's a couple ways that we know. We could say that there's a constant rate of change. We can see that there's a constant rate of change. We can see that here in the table. It's going up 4 over 1, up 4 over 1 consistently through the whole table. We can also see that the graph makes a straight line. And having all these different representations just verifies that all of this goes together. Every single representation verifies that we have linear. We have a straight line with a constant slope. We have a constant adding pattern in the table, and our equation fits the format y equals mx plus b. So that scenario was me giving you a context and you coming up with a graph, a table, an equation. I can also start you with something different, like down here, there is a context here. An airplane is at an elevation of 3,000 feet. So the elevation is in feet. This is our starting point now. The table shows its elevation for every 2 miles it travels. So I am giving you, in this scenario, I'm giving you a table and you're going to work from a table. So you might be given any one of these representations here. If I give you one, you should be able to come up with the rest, but all of them should verify in your work that it is linear. So here, okay, so what I see in my table right here is I see, and I'm actually going to draw this here because I'm going to need this. I'm going to look at the rate of change here. I see that this actually goes down 1,000 and then down 1,000. And as this goes down 1,000, this goes up 2, up 2. This means to me that I have in this scenario, I have, and I'm going to write this over here. I have a negative rate of change. Okay, and when you have a negative rate of change, what that means to you is that you have a decreasing scenario. Sometimes we think, and this is when we were looking at the linear pattern, some of you wanted to say, well, stage 0 is 0 because our blocks can't go in the negatives. Well, absolutely they can, and negatives have real life scenarios. Okay, in context, negatives mean something in real life. And with the rate of change, if you have a negative rate of change or a negative slope, that means that whatever's going on, however it's changing, it's decreasing. Okay, so that has a real life context, and we're going to use that right here. We're going to show ourselves that we have a negative context. Sorry, just touched that weird light centering thing. Okay, let's turn this into a graph first. I'm going to let the x-axis be miles. And I see it goes 0 to 4, and these boxes are not too squishy, so I can just label them, and I have plenty of room. I'm just going to go up to 10 there because that's what I have. Now, this elevation is going to be elevation in feet. Now, I am going to label it. I'm actually going to label it over here this way because that's a little bit squishy for what I need to write. So I'm going to say this is elevation, and it's elevation measured in feet. Okay, so let me scooch this over a little. And what I see is this one's going to start at 3,000. I have 1, 2, 3, 4, 5, 6. So guess what I'm going to do? I'm going to do 3,000 divided by 6, which is 500. Can you see how this would nice and easily fit? This would be 1,000 here. This would be 2,000 here. And that means in between, these are each going by 500s. Okay, we all okay with that? And then as I look at that information from my table, I can see that this initial value is 3,000 in this linear relationship. And from there, it goes down 1,000 for every 2 miles, right? Or even if I just follow those ordered pairs, 0, 3,000, 2, 2,000, and 4, 1,000 puts me about here. And look, that actually means I'm hitting every one of these corners in between, and I can just keep that pattern going. I can keep that going there. Okay. And what I now see in the graph is the same thing that I see in the table. I see that, yes, this rate of change here is going down 1,000. Sorry for all the wonky angles here. Down 1,000 over 2. 1,000 negative 1,000 over 2 is, of course, also what I see in the graph right here. I see that the graph is going down 500 over 1, down 500 over 1. That's also what I get when I divide this. So the rate of change is negative 500 feet per mile. What does that mean? That means for every 500, for every mile it's flying horizontal distance, it's changing a vertical distance of 500 feet. Okay. All right. Let's write an equation for this relationship. So I now have rate of change, which is m. So I'm going to say y equals mx plus, what was the starting point here? 3,000. 3,000 feet at 0 miles when they started measuring this. Probably when they started their descent. Now look at this. Use the equation to find out when the airplane will hit the ground. Well, what's the ground? The ground is elevation 0, right? And elevation is y. So we're trying to find out when will y equal 0. Because I'm left-handed, it's easier for me to write if my paper's slanted this way, if you're wondering why it's like that. So what I'm going to do is I'm going to take my equation and I am going to plug in 0 for y. I'm going to replace the y with a 0. So I'm going to go 0 equals negative 500x plus 3,000. And now I'm simply going to go through my basic solving equation steps. My phone froze again, which means it's probably about to go to sleep. Yeah, hi, come back. There's some things on my phone that you guys can now see. Okay, so now I'm going to go minus 300 minus 300. This is negative, why did I write 300? Honestly, 3,000. I don't know why I wrote 300. Minus 3,000 minus 3,000. So this is negative 3,000 equals negative 500x, which at first seems weird. We're like, why do we have all these negatives? Because it's all going to work out right here, because now I'm going to go divide by negative 500, divide by negative 500, and negative 3,000 divided by negative 500 is positive 6. Now, what does that mean? The plane will reach the ground after 6 miles. And see how this connects. It asked me to use the equation to find that. I could have also seen that in the graph here. I can see that elevation 0 down here on the graph is happening at 6 miles. Okay, so your Canvas quiz is going to have you practice this idea. If I give you one format of a linear, I might give you a table and ask you for an equation. I might give you a graph and ask you to make a table. If I give you one format, can you give me a different format and maybe even answer a couple questions? You're going to practice this on your Canvas quiz, and you're also going to practice this a lot tomorrow. All linear representations. If you have any questions at all, please ask your math teacher.